All right, zoning. We've talked a little bit about this. Do we zone with zone pumps or do we zone with zone valves? And or why would we even zone a house? Okay, your typical house that you would move in today generally has an HVAC system, right? And you have one thermostat and you run the whole house. Pretty standard, right? Should we do that with a radiant system? One thermostat for the whole house? Some shaking heads. No. Okay, what are your thoughts? Why not?
So if you do one, you can't control each room.
Okay, right. So what if I build a house that is master bedroom south facing and kitchen north facing, and I put the thermostat in the kitchen? What happens with that master bedroom?
So
You get solar gain, right? Okay. Anybody know about solar gain? You know how many times I get chewed out at a job site saying my system's overworking, and come to find out because this whole wall is glass and they're saying that my radiant's working, but yet the thermostat's set at 60 degrees and the room's 80. Do you think the sun never does anything? Okay. You jump in your truck in the middle of summertime. Yeah, how hot is it inside your truck? If you don't roll the windows down, right? Okay. Solar gain does a huge deal to our houses and our systems. Okay. So a benefit to zoning a system, whether it's HVAC or radiant, is we can get a little bit better controlling out of our houses, right? Okay. That's what we're doing here. Now, this particular question here on the screen, though, is saying, are we going to zone with zone valves and actuators, or are we going to zone with zone circulators? Now, do we want to do fixed speed circulators? We want to do variable speed ECM circulators. Okay, big, huge question. We've already talked about it. Okay, who wants to answer? Who wants to do pumps and who wants to do zone valves? Or can we do a mix? Who wants to do what? Okay, is one better than the other? Depends on the system, right? Okay, just depends on what you're doing. So, why should we even consider doing multiple zones? Do you want your master bedroom the same temperature as your kitchen? Typically not, right? Okay. Generally, most people will sleep, they want their sleeping area, their bedrooms cooler than they want the living areas, right? Okay. Now, what about your master bedroom and your master bathroom? Can you split those out? Do you want to split them out? Okay, you know how many architects and plans I look at that don't do that? It drives me crazy. Okay, you might as well. You're already putting in a radiant system. The only thing you got to do is just make sure that the tubing in this room doesn't go into the tubing of that room. You throw a thermostat on each wall of those rooms and now you're separated, right? Okay, how you want to connect that, either one manifold or separate manifolds or whatever, is up to you, but yeah, you might as well, when you're running tubing and starting to lay tubing down, you might as well keep every room tubed on its own set of tubing circuit, right? And then if at first they don't want to zone it, then at least you've tubed it to where you can separate it. Maybe you run some thermostat wires depending on what you're doing, okay? But you can try and pre-prep, or as you're going through the system and you're talking with the homeowner, you can say, hey, Mr. Homeowner, this will be a better benefit. You'll be better off, right? Okay. So, what is the best way, pumps or zone valves? Just depends on what you want to do. All right. Anybody seen some zone valves that look like these guys? Yeah. Go back to the old Taco ones. Those are some older ones. They had all sorts of different styles with the old Taco. They still offer Taco like that?
They just discontinued.
Oh, do they? Ah. Are they just staying with the greenhead guys now, the Centuries? Okay. You can get them in sweat. You can get them in thread. You can get them in press. The old Honeywell ones, you can get them with the wire leads on them. What about that one? What about this little blue guy? Where would that guy go? Okay, top of the manifold, right? Okay, who knows the term? So these ones are all called zone valves. what do we call that one? Or, yeah, that one.
Well, actually,
Actuators, correct, yes. Okay, and they go on manifolds typically. Okay, now you can put, so say you've got one manifold, well, you've got 3 manifolds. Each manifold does its own room, but you're going to supply one pump. You could do some zone valves on your pump board down in the mechanical room, but let's say they put us in a closet so we don't have any room. You can get these little actuator guys that would go on the, you can put it on the supply or return side, but you can get those and just do one, and then you could control your manifold off of that.
do those just fit on a standard manifold, or do you got to buy like a special deal? That
So you have to buy the manufacturer's actuator zone valve for manifold.
like fit
No.
like a special one.
It kind of goes just manufacturer to manufacturer, yeah. Some guys cross, some guys don't. So it just depends on whatever manifold is at the job, then you should stay with that brand and go to,
I guess just to
go to them.
run into a situation where maybe like
Right.
you got to just change the whole manifold, or can you, or does it just fit carrying this one? Yeah.
Well, yeah, but because even Watts doesn't fit the Rayhow though, right? Do they?
Made by the same company.
Okay.
Same with Luminous. That's why they say carry the last one.
Now, does this style fit? This doesn't fit the same ring. Isn't that Uponor specific manifold?
Your R32.
Are they? Okay. So maybe you could. Okay. I was always confused that.
Last 5 years.
Okay. So maybe I'm thinking some old ones could.
Vegans do not fit anyone else's.
Yeah, Viga's kind of that way. They like to be on their own. So, and that's I do all Viga. So we don't like Rayhow. Just kidding. Okay. He's a Rayhow guy, by the way. Can everybody know who Rayhow is? So, okay, let's go off another tangent here. Rayhow, so Rayhow PEX is what type of PEX? A, B, or C?
Oh, yeah, so
Yeah. Okay, so PEX A.
embedded pegs.
Okay. Who knows what style PEX A for their fittings? What are you supposed to use? What are they designed for? Do you remember? We talked a little bit about the difference of PEX A, B, C, but...
PEX is the expansion fittings, right?
Okay, PEX A is the expandable type PEX. Okay, so Uponor, Rayhow are the major guys. You can do Mr. PEX too, but they kind of like a crimp style really on theirs. But who else do we got this PEX A? So Mr. PEX, Heatlink was another one. But even Heatlink's fittings were they were a crimp style.
Well, they both
expanded.
But they both allow the cut.
Yeah, but you can do it. So everybody heard the term F1960 in fittings when you're talking about fittings. So if you ever hear somebody at PEX or the wholesaler, somebody say, hey, I need an F1960 fitting, that is just the fitting that takes the expanded PEX A type PEX connector. So there's a ring, a sleeve that slides over the pipe, and then you insert the tool and expand it, physically expand that pipe, and then you fit the fitting inside of it, and then it'll shrink back down onto the fitting and lock itself into place. Okay. Rayhow makes another type of fitting that is similar to that, where you expand it, but it's got a hard sleeve that goes over. You expand the pipe only, put it on the fitting, and then you take another tool and it grabs the fitting in that sleeve, and it pulls the sleeve back over the pipe, and what they call it an Everlock fitting. And
See video of that, UK.
yeah, it's almost like a guaranteed no leak fitting ever, but the tooling and everything it's kind of a pain in the butt, really, honest.
It's like a press.
In my opinion. Yeah, Milwaukee, I mean, they've come out with tools for it now, so it is easier, but it is a longer process to do it, right? So it just depends on what you like. I mean, I highly suggest try all the brands out there and just find one that fits for what you like to do. okay? Because you've got PEX A that's expandable. You got PEX B, which is just a crimp, really. But you've got Viga's crimp style. You've got HeatLink's crimp style. You've got the regular copper ring crimp style fitting that you just get everywhere. God, I don't know. I personally like Viga's PEX press style. So you get an Impex press or Pro Press or Mega Press, right? Everything for them is a press. But I like their press fittings. But at the company I work for right now, we use mainly Ray Howe, and everything's expanded. So fittings are a little bit more than just your regular crimp ring, but I think they're a better fitting and they seem to hold up better. But the only part that really sucks is when it's cold. Then you got to have a heat gun and you got to give it some heat so it'll shrink back down.
I guess with your since you're I guess with the crimp style, you're much smaller diameter. Like, does that actually affect your pump sizing at all? Like,
yes.
Versus crimp it?
Yes. The answer is yes, but that is something that is always argued between manufacturers. So how much it affects depends on the fitting, because there are some brands out there that have a thicker fitting, so you get a smaller inside diameter fitting. There's others out there that keep the fitting to a minimum thickness, and so they try and keep that inside diameter smaller. The claim for Ray Howe and Uponor type fittings is they're claiming they keep that inside diameter the same size as the PEX, so then you don't get that restriction of that fitting coming through. Make sense? Okay. Yeah, so their claim is you don't get that extra resistance other than the 90 of just hitting the 90 wall, right, and going through, but you won't be hitting that fitting and going into that reduction. So you can take that into consideration. I mean, if you want to get down to the engineering technical terms of it, then yeah, maybe you want to keep that in mind. So
Isn't this that's much people at 20?
right, yeah. When you're laying tubing in the floor and your wire tie gun or your hammer or something falls and pokes a hole in your tubing, do you coupler that tubing before they pour concrete, or do you rip that run out and replace it?
Is it a Friday?
Yeah, like is it a Friday, right? Okay, but what should we do?
Good places again.
Okay, yeah. So, right, is it Friday at 5 o'clock when you're getting the service call too, and now you got to head back up to Park City? Okay. So, yes, if you hit the tubing, whether you're doing staple down or it's in the slab, and you poke a hole in it, you can coupler it. If you do coupler it, stay with whatever brand tubing you're using and use their fittings, because then you will keep their warranty with that tubing. But if you do have the chance, I would rip it out and I would replace it. I can't tell you how many times I've done that. So it's a pain in the butt, especially on staple down. Seems like in slab, either zip tie or wire tie guns, you never have a problem. But yeah, no stupid staple guns. It seems like they'd always curl one every now and then, and right in the side of your tube, right at the last 5 feet of it too, right? When you're finishing up. Okay. All right. I don't want to go too much into this because it gets crazy trying to understand it and figure it all out. But so we talked a little bit last week. We were talking about head loss, right? What were the two things that we need to size the pump?
Yeah, right.
There was two different pieces of information we needed so we could size the pump. Who remembers what they are? You need to know how much GPM you've got and then how much head loss you're trying to overcome, right? Okay, so you need GPM and head loss. When we're talking about zone valves or ball valves, gate valves, I mean, all those type of valves, they generally are rated with what's called a CV rating, okay? Easy term, CV is just another term for head loss, Okay, it's just how much friction is going to go through that fitting, that valve, and it's going to create how much restriction to push through it depending on how many GPM you're trying to push through it, right? So the higher the GPM, the higher your CV rating, your head loss is going to be on that particular piece of equipment, that valve, right? So when you're designing your applications for zone valves, you need to consider the amount of CV, head loss, that your valve is rated for so that you can size your pump accordingly. Okay, so, yeah, so let's see. So valve flow coefficient is what CV stands for. So is the flow capability of a control valve at fully open conditions relative to the pressure drop across the valve. It is defined at the volume of water, your GPM, 60 degree Fahrenheit, that will flow through a fully open valve with a pressure differential of 1 psi across the valve. Okay, a lot of information, right? Okay, now there's a fun equation that you can do to figure this stuff out if you really want to get technical with it. Do you guys remember the charts that I showed when we were talking about your pressure drop in PEX tubing? Right, we were using that chart where 1/2-inch PEX tubing at a half a gallon creates, whatever 0.01 or whatever it was pressure per foot, right? Okay, so this is kind of the same concept as you're going to create pressure depending on your flow rate. So your equation here, you got the PD equals your Q times your, oh my heck, I just went totally blank on that one. Okay, so you've got water pressure, so your pressure drop across the control valve, so PSI, your water flow rate in gallons per minute, your flow coefficient, and then your specific gravity of fluid. Now remember, your specific gravity of fluid is going to change if we're going to use glycol. And it's going to change depending on your glycol percentage. And it's going to change depending on the temperature of that glycol. Okay? So you got all these different variables that you're going to have to do. So just, like I said, I don't want to go too crazy in depth. I've given you this calculation. If you're a math genius, I'm not, then here you go. There's some stuff for you, okay? So just keep that in mind. But now, oftentimes with some of these zone valves, you don't always have to keep the same body size of, so say you've calculated 1-inch PEX tubing that you've got to run from your boiler room out to your manifold, okay? Just because the PEX tubing size is 1 inch doesn't mean that you're going to go find a 1-inch zone valve and throw into that system. Although that's what we do, but you don't have to. Sometimes you can go down in size. Sometimes you might have to go up in size depending on what your flow rates are, okay? So there's a lot of stuff to consider that way. All right. Does your zone valves go on the supply side or the return side? This drawing shows them on the return side. Doesn't matter which side they go on. Okay, got somebody shaking his head no. It's kind of a trick question because I think it does. Depending on that guy. If I went old school and got a $26.99 and I put them on the supply side, I've always experienced water hammer because that's a fixed speed pump that's pushing all that pressure, and all of a sudden I took a valve and shut it off. Okay, now technology's kind of changed though. Our motorized actuators are a little bit slower reacting so that they don't just slam shut, right? But I've still noticed the same concept though. If they're on the supply side with a fixed speed pump, I always got some water hammer in my system. But if I moved them and put them on the return side, like the drawing shows, I got rid of that water hammer because now I've made the distance from here to here greater. And so, and so you have that buffer of piping for the fluid, right? And you wouldn't get the water hammer. But if we're going to go with the new circulators that we have today, the ECM circulators, they're variable speed. They have the sensors in them to pick up who's opening, who's closing, how fast it needs to go, how slow it needs to go, right? So it's sensing when these guys are starting to close, so it starts to slow itself down. As soon as that valve closes, well, now the pump either slowed down enough or it stops if they're all shut, and you don't get that water hammer, okay? So for me, yes, it would matter if they're on supply or return, depending on what pump I'm using, okay? But if I was going to use a 2699 pump or a fixed speed pump and I'm going to use zone valves, I wouldn't pipe it like this anyways, okay? You would have to have a bypass loop that would be able to take up the pressure and the flow that pump's creating when not everybody's on, right? Okay, but I haven't seen a system, what were those called, bypass valves? I haven't seen a bypass valve, pressure differential bypass valve. I haven't seen one of those in years, though.
So yes.
Oh, yeah? Wow, nice. They're still around, okay? So if you were going to do this in this example here, and if this was a fixed speed pump, you would need basically another T that came off and came directly over here and back in. And what that differential bypass would do is if only one zone valve is on, then the excess pressure and flow that he's going to create would go through that bypass valve and just go right back through himself, okay? And then if all of them are open, nothing's going through the bypass valve, everything's going through the system. That's just the purpose of a bypass, okay? So, all right. Let's look at a little bit of an example here. Time are we? 7 o'clock. All right. Everybody good for a minute? Still okay? Okay. You lost your drink? All right. Okay. So let's play with a little bit of an example here. This one, let's see. I think this one I gave you the equation in your book on this, right? Yeah. So this is the one where this has this crazy funky equation on this one. So if you have a zone valve that has a CV rating of 7, so that means that at a flow rate of 7 GPM, there will be 1 PSI pressure drop through that valve. The 7 is not the maximum flow rate that you're going to be able to push through this valve. The valve could flow up to 15 GPM. But your pressure drop is going to increase because we're going to increase our GPM. So if we went back a little bit, remember our equation, okay? So 1 PSI, and if we go back to last week, 1 PSI equals 2.31 feet of head. Remember that one? So at 15 GPM through this valve rated at 7 CV, the pressure drop will be what PSI? Now this is where it gets tricky because now you got this equation. Okay, so here's our top equation. We're going to rewrite it in the numbers we've been given, right? So you got your 15 GPM now. The valve is rated at 7. This is where it got a little funky. So I took and flipped it just so it made sense to me. So this should be in your book, right? Did I give you this? Oh, I didn't give you this one? Okay, so you can write that one down then. So I just flipped it so I could read it so I could start to solve it. Okay? So I'll let you guys take and write that down for a second. So at 15 GPM, with a valve that was rated at 7 CV, our pressure drop in PSI is going to be 4.59 PSI. Okay? Now, this is PSI. What did we have to do with PSI again? Because we're looking for foot of head. Right? So I gave you your equation back up there again. So what do we need to times a PSI by? So we got 4.59. We're going to times that by 2.31, and that'll give us our foot of head from the PSI. Okay, because everything we're doing here in this calculation, this is all just to find what pressure drop, PSI, we have through that valve at the given flow rate that we have. Okay. Okay, I can still see some of you guys writing stuff down, so. All right. Okay, who's at the converted? So we converted. So PSI to foot ahead. Who's done that calculation yet? So who's got 4.59 times 2.31?
I guess on 6.
Okay. So you got 4 point, I rounded up. So 4.6, but yeah. So same thing, 10.6. So you take 4.6 or 4.59, times it by the 2.31, you get 10.62 feet of head. Okay, so now there's your calculation, your foot of head, that you're going to be able to use to size your pump. What was our GPM?
Done.
15, right? So our GPM, so if we needed, so now we want to size a pump that will go through this zone valve and our system. So we just figured out that we need 15 GPM at 10.6 feet of head, basically. Okay? So if we went back to, remember all of your little pump examples, your little pump charts? Okay? So now if you went back to this, you've got 15 and 10.6. Okay? What pump would you use for that one? 1 through 5. So let's look at that real quick. Since we're here, we got a minute. Okay, so look back, starting with pump 1, 2, 3, 4, and 6. Which pump would you use to do that 15 GPM and the 10.6 foot ahead? Is everybody back to pump 1 and 2 page? Getting there. So there you go. Keep going. Okay. Would example pump number 1 work? 15 and 10? Nope. It's too small, right? Okay. What about number 2? Can we use number 2? 15 and 10?
Yes.
Okay. We could, but is it anywhere close to any of those 3 lines? Not really, right? Okay, so if we did use number 2, what would we do? Remember, it was 1, 2, and 3 speed on the lines, the curves, right? So if we went with pump number 2, it falls in between 1 and 2 line, right? So what would we do if we used that pump? You've got 1, 2, and 3, and we're kind of in here-ish, right? Okay, if we selected this one, what would you select? 1, 2, or 3 speed?
Yes, I do.
You want to go down to 1? You want to go to 2? Okay, what happens if we go to 1?
Then we'll disperse heat better to that pumps. We were talking about how fast it all moves through the system.
Right. Okay.
On the lower speed.
Okay, so if you go on the lower speed, just looking at our chart here, let's say, yeah, so we're about 15 GPM-ish there and 10, give or take there, right? Well, we'll say 11, whatever. 10 and 11, we're in that range, right? So if you picked speed 1 with this pump, you're going to move down here, which changes what? What's happening on the bottom of our curve here?
The GPM is lower.
Okay, now we just changed our GPM to... Let me follow the real chart. So it actually pulls it clear down to 9 GPM to hit that mark. Okay, so now you've slowed your flow down to 9 GPM versus 15 GPM is what we initially calculated at. Okay, so is that good or bad? It's probably going to be bad because now you're not moving the fluid fast enough for what you were designed to try and do, right? Okay, now let's go opposite. What if we go up to speed 2? That's going to push us up to with 10. That puts us up here at about 18 GPM. Okay, so now if we increase our GPM, what do we have to recalculate? Now you have to go back and recalculate what you just calculated because you calculated it for 15 GPM. Now you're going to try and push 18 GPM through it. So what happens? What increases with the GPM? Your head's also going to increase too, right? Okay. So would pump 2, would you pick this pump if that's where we started at? Okay, I wouldn't, right? It's nowhere close to what this circulator can do, okay? All right, so what about chart 3? Let's see, what does 3 give us? 3 gives us 15 and 10. Need to take those funky loops out of there. But yeah, so this one doesn't really work either, right? Okay. What's that?
It's just a, oh,
Yeah, do you see the little squiggly lines on that one? Okay, what about pump 4? 15 and 10, does that one even come close? Nope, it's outside the range on that one too. So far we don't have any luck with any of these pumps we got. So let's go to pump 5. Can we use pump 5? 15 and 10, we could. So 15 and 10 on that curve, it's pretty decent, right? Okay, what about pump 6?
yeah.
We could do pump 6 too, right? Okay, so out of all of those, with what we calculated, we could use either pump 5 or pump 6. So now you're going to call your wholesaler, you're going to see what's available or what the cost is, right? Okay. All right, everybody kind of following? Making a little sense? Okay, if it's not, ask questions. That's what we're here for. Oh, okay, yeah, so just to finish off your example, so if you have 15 GPM, then you will add about 10.6 feet ahead, or round it up,